In IR spectroscopy, we assume covalent bonds are nothing but springs. So when spring vibrates, then its frequency is guided by Hooke's law. Now let us consider what is the mathematical representation of Hooke's law, that is nu is equal to 1 by 2 pi under root of k by m, where nu is equal to frequency of vibration, k stands for force constant and m stands for mass of the atoms connected by covalent bond or the spring. Now if we investigate this Hooke's law, then it is clear that frequency is directly proportional to under root of force constant and it is inversely proportional to the square root of mass. It means that frequency is higher if the force constant is higher. A force constant in its turn represents the strength of the bond, means the stronger the bond, higher will be the K, higher will be the frequency. Now coming to the mass, heavier the mass, lower will be the frequency. Lighter the mass, heavier will be the frequency. So in place of frequency in Hooke's law, it can also be expressed in terms of wave number, means Hooke's law can be expressed in two forms. One is in frequency form, another one is the wave number form. So now let us see, if it is expressed in wave number, then what modifications are there in Hooke's law, and in that case nu bar, means the wave number, is equal to 1 by 2 pi c under root of k by mu. Now what is mu? Mu is nothing but the mass, but specifically it is called as the reduced mass, where mu is equal to m1 into m2 divided by m1 plus m2, where m1 and m2 are the mass of the two atoms connected by the covalent bond or spring, which is equally applicable to the previous form of the Hooke's law also. Now let us take few examples and try to apply Hooke's law, and let us check how Hooke's law is very useful to understand the frequency or the peak positions in IR spectrum. Now the first example, we will try to take the three bonds. One is the carbon-hydrogen bond, which is attached by the single bond. Next is the carbon-deuterium bond, and there is a single bond. And the third bond is the carbon-carbon bond, which is also a single bond. Now CH, CD and the CC, the difference, if we check the difference is in these three bonds, one bond has hydrogen, second bond has deuterium, and the third bond has carbon, and all of them are single bonds, so there will be no difference in the bond strength, means approximately the K, means force constant, will be same. So the difference will be in the mass, means the reduced mass. So lower the mass, higher will be the frequency, means out of CH, CD and the CC, hydrogen will be having the lowest mass, followed by deuterium, and the heaviest will be the carbon. So therefore, according to Hooke's law, the highest frequency or the wave number will go to the carbon-hydrogen, followed by carbon-deuterium bond, and the lowest frequency or wave number will be seen in case of the carbon single bond C. Now if we see the right column of this table, then we can see that carbon-hydrogen bond appears at 3000 centimeter inverse, carbon-deuterium bond appears at 2100 centimeter inverse, and carbon-carbon single bond appears at 1200 centimeter inverse, which can be explained by taking the help of Hooke's law. Now we will take the second example where we will take the carbon-carbon single bond, carbon-carbon double bond and carbon-carbon triple bond. Now in this case, there is no difference in the atoms, the mass of the atoms, because in all these three cases the atoms are only carbons. Then where is the difference? The difference is between the bonds. One case carbon-carbon single bond is there, second case double bond is there, and the third case triple bond is there. Means there is a difference in the strength of the bond. Means the triple bond is the strongest, double bond is the medium, and the least strength goes to the carbon-carbon single bond. And we know the strength of the bond is connected to the force constant. Stronger the bond, higher will be the force constant. So for the force constant, the triple bond will be having the highest value, followed by the double bond, and the lowest value for the force constant will go to the single bond. So we know from the Hooke's law, force constant is directly proportional to the frequency or the wave number. So therefore the triple bond will be having the highest frequency, double bond will be having the second one, and the lowest value will go to the C single bond C. Now if we check to the right column, then C single bond C appears at 1200 centimeter inverse, C double bond C appears at 1660 centimeter inverse, and C triple bond C appears at 2200 centimeter inverse in the IR spectrum, which can be explained in terms of the force constant order and then connected to the Hooke's law. Now let us take the third example where it will be the similar type of thing. Means the peak position will be guided by the force constant, where we are taking the carbon nitrogen, two atoms. These two atoms are connected by single bond, they are connected by double bond, and they are connected by the triple bond. So triple bond has the related force constant maximum, so the peak position also will be following the same trend. Means the C triple bond N will be having the highest frequency or wave number, and the C single bond N will be having the lowest frequency or wave number. In between we will be having the C double bond N. So if we see their peak positions, C single bond N is 1200, C double bond N is 1650, C triple bond N is 2200 centimeter inverse. Now instead of carbon or nitrogen, if we take the oxygen, means carbon single bond oxygen and the carbon double bond oxygen, exactly similar trend will be seen, which can be explained in terms of the force constant of this single bond and the double bond. Force constant for the double bond is more, so therefore frequency or the wave number also will be more. Force constant of C single bond O is less, therefore frequency or the wave number also will be less. Now let us take that another example of the application of the Hooke's law, that is carbon hydrogen single bond. In all the cases we are taking the carbon hydrogen single bond only, but the hybridization of the carbon is different in the three cases. In one case carbon is sp3 hybridized, in another case carbon is sp2 hybridized, and in the last case carbon is sp hybridized. Means when carbon has 4 sigma bonds, then that is carbon is sp3 hybridized, and the percentage of S character is 25% in that hybrid orbital. When the carbon is doubly bonded, then carbon is considered as sp2 hybridized, and the percentage of S character is 33% of that bond. And when the carbon has triple bond, then that carbon hybridization is sp, and the percentage of S character is 50%. We know that stronger the bond, higher will be the percentage of S character, because the S orbital is closer to the nucleus, so it will be having the more control, the more attraction over the nucleus. So if the percentage of S character is directly proportional to the strength of the bond, then in turn strength of the bond is directly proportional to the force constant. So therefore we can correlate, higher the percentage of S character, higher will be the force constant, higher will be the frequency or the wave number of that particular stretching vibration of the different CHs which are connected to the differently hybridized carbons. So based on this, if it is carbon is sp3 hybridized, then it will be having the lowest peak position, and if it is carbon is sp2 hybridized, then it will be having the higher value than the carbon which is sp3 hybridized, but it will be having the lower value than the sp hybridized carbon, the hydrogen attached with the sp hybridized carbon. So overall order will be, the highest value will go to the CH stretching vibration which is attached with the sp hybridized carbon, followed by the CH stretching where the carbon is sp2 hybridized, and the lowest value will go to the carbon hydrogen stretching where the carbon is sp3 hybridized. Now let us take the another example, that is if the atom is replaced by its heavier isotope, like hydrogen is replaced by deuterium, or the C12 is replaced by C13 or C14, oxygen 16 is replaced by its heavier isotope O17, that nitrogen 14 is replaced by its heavier isotope N15, then how the peak position will change in the higher spectrum. That also can be understood by applying the Hooke's law, because when we are replacing the atom by their heavier isotopes, then reduced mass will become heavy, and if the reduced mass becomes more, then we know by applying Hooke's law the peak frequency or the wave number of the particular vibration will be inversely proportional. If mass becomes heavy, then the frequency or the wave number will become less. Now take it for granted, one example, CH versus CD. Now CH stretching vibration appears approximately at 3000 centimeter inverse. Now when the hydrogen is replaced by deuterium, then this reduced mass of CD is more compared to the CH, and so therefore the stretching vibration of CD will appear less than 3000 centimeter inverse. Actually it comes at 2250 centimeter inverse. Now let us go to the functional group identification by considering the peak position in the higher spectrum. Now first is the let us consider the peaks which comes in between 4000 to 2500. Usually the carbon hydrogen bond, oxygen hydrogen bond, nitrogen hydrogen bond, and the sulfur hydrogen bond, they only usually they appear in between 4000 to 2500 centimeter inverse. Now in this we have to consider that if we have the carbon sp3 hybridized, carbon sp2 hybridized, and the carbon sp hybridized, then based on Hooke's law, which already we have discussed previously, we know that the carbon hydrogen bond which is having sp3 hybridized carbon will be having the lowest frequency or wave number, and the carbon which if it is sp hybridized, then it will be having the highest wave number. So as for example here, it is, if it is sp3 hybridized, that will come approximately 3000 or below 3000. If it is sp2 carbon hydrogen stretching, which includes aromatic carbon hydrogen stretching also, that will be approximately 3100 to 3000 centimeter inverse. If the carbon is triply bonded, in that case carbon hydrogen stretching will appear approximately at 3300 centimeter inverse. Now coming to the OH stretching, OH stretching appears in between the 3650 to 3200 centimeter inverse, and it is not only the peak position, OH peak is very characteristic in IR because it appears as a broad peak, not as sharp peak. Now coming to the SH stretching comes in between 2600 to 2500 centimeter inverse. Now if the OH of carboxylic acid is there, because the OH is present in the alcoholic OH, phenolic OH and carboxylic acid. Now if OH is the part of the carboxylic acid functional group, in that case it will be having the lower value than the OH stretching of alcoholic OH and the phenolic OH. It will come little down, it comes. Now NH stretching also comes in this zone, and then 3500 to 3300 NH stretching comes. The aldehyde also has a very characteristic CH stretching that comes approximately 2800 to 2700 centimeter inverse. So these are all about the various types of XH stretching, where the X can be carbon, oxygen, sulfur, nitrogen, etc. So now coming to the functional groups which appear in between 2500 to 2000 centimeter inverse, and this part is very characteristic because only two types of groups which gives the peak in this zone are C triple bond C and C triple bond N. So if our molecule contains the alkyne group, otherwise if it contains the cyanide functional group or the nitrile functional group C triple bond N, only in that case only we will be getting the characteristic peak in between 2500 to 2000 centimeter inverse. Now coming to the functional groups which give the characteristic peaks in between 2000 to 1500 centimeter inverse. Usually all the varieties of the double bonds, like the C double bond C, whether it is isolated or conjugated, or if it is the aromatic, then if it is the C double bond O, usually they C double bond N or C double bond S, all these things where the atoms are connected by a double bond, those things usually gives the peak in between 2000 to 1500 centimeter inverse. Now coming to one of the very important functional group which can be easily understood in by referring the peak position in IR spectrum is the various types of C double bond O. Now this C double bond O can be present in various functional groups, like it can be present in ketone, aldehyde, carboxylic acid, ester and acid halide. So all these things can be well understood by referring the group frequencies of those functional groups. Now coming to the ketone, the ketone and what it is, the ketone usually appears in between 1725 to the 1705, and the standard value for the ketone is the cyclohexanone or the acetone, which gives the peak for C double bond O stretching frequency is 1715 1715 centimeter inverse. Now coming to the carboxylic acid C double bond O also appears in the same zone only, but carboxylic acid will be having one additional portion, that is OH stretching, which will not be there in case of the ketone. Ketone will be having only C double bond O stretching, but the carboxylic acid will be having C double bond O stretching plus OH stretching. Now coming to the aldehyde appears slightly higher than ketone and the carboxylic acid. C double bond O stretching frequency of aldehyde is approximately 1740 to 1720 centimeter inverse. Ester also appears in the higher values, approximately 1740 centimeter inverse, and acid halide appears at the even higher value than the ester. And coming to the amide is C double bond O stretching frequency of amide appears at the lower value, approximately 1640 to 1690 centimeter inverse. Now in addition with that, anhydride is also one functional group where the C double bond O is present, but in anhydride we have the two C double bond O which are connected by the oxygen. So in this case, C double bond O comes, actually two stretching frequencies comes in the higher side, approximately 1750, and another one is approximately near about 1800 centimeter inverse. 2 C double bond O stretching frequency comes for anhydride functional group, that is due to the antisymmetric stretching and the symmetric stretching of C double bond O. Higher value goes to the asymmetric or antisymmetric stretching, means near about 1800 centimeter inverse. The peak which appears for the anhydride C double bond O is due to the antisymmetric stretching, and near about 1750 centimeter inverse which C double bond O stretching frequency appears for the anhydride functional group, that is due to the symmetric stretching. Now coming to the peaks which appear in between 1500 to 650 centimeter inverse. Now in this zone, the stretching frequency for the single bond appears which are not XH stretching, means XH stretching comes in the 4000 to 2500 centimeter inverse, other than the single bonds like carbon oxygen, carbon nitrogen, carbon or various types of single bonds where hydrogen is not the partner, they appear in this zone, and the bending vibrations appear in this zone. So all the bending vibrations appear in this zone along with this stretching of the single bond appears, and this particular zone is popularly known as the fingerprint region. Means it is exactly like a human being. For human being, fingerprint is considered as a unique for one person. So in a very similar way, if the compound is similar, then only fingerprint of the eye will be similar. If the compounds are different, fingerprint region will be different. So this fingerprint region is useful to understand the identity of the molecule. If the molecules are identical, exactly same, then fingerprint region will be same. If the molecules are different, it doesn't matter whether they have the same functional group or not. If the molecules are different, then fingerprint region will be different. Now another very important application of the fingerprint region is we will be able to know in the aromatic compound. In the benzene ring, is it a monosubstituted compound or not, means the only one group is there or not in the benzene ring. If it is a ortho para or for the disubstituted compound, if it is the meta groups are there, the ortho or the para groups are there, those things can be understood by seeing their peak positions in the fingerprint region, and those peaks are popularly known as, which are very characteristic to understand the substitution pattern in the benzene ring, like the monosubstituted one, or among the disubstituted, is it ortho disubstituted, is it meta disubstituted, or is it para disubstituted. They are popularly known as the OOP bending peaks, means out of plane bending peaks. Now they usually come in between. If it is a monosubstituted compound, then you will be having approximately 750 centimeter inverse, you will be getting the strong peak. If it is a meta disubstituted compound, then usually you will be having the higher side key peak will come. If maybe it will be approximately 700 to 800 here it will come, and for the ortho and the para benzene, little lower side key the peaks comes, that is in between 650 to the 720, like that range key the OOP bending peak appears, which are sometimes, not always, but sometimes they are very useful to understand the substitution pattern in the benzene ring.